गुड इवनिंग फ्रेंड्स, कैसे हैं आप लोग? लगता है सब ठीक ठाक चल रहा है। टुडेस टॉपिक इज वेपर पावर साइकिल। वी ऑल नो दैट व्हाट इज वेपर पावर साइकिल. Mainly uses in thermal power plant. क्या काम होता है वेपर पावर साइकिल का? From the naming you can observe that it is ultimately a power cycle. Means हम लोगों को क्या करना है? We have to put out an mechanical work from that cycle. It is also called as a Rankine cycle. It is ultimately a thermodynamic cycle. What is thermodynamic cycle? Thermodynamic cycle means if we consider a PV diagram, then if it is a cyclic process, suppose the condition is 1 to 2, 2 to 3, 3 to 4, means where this fluid medium which operates through the cycle and then condition at 1 is P1 and V1 and whatever the temperature is, suppose it is T1, is after getting through the so many process 2 to 3, 3 to 4, 4 to 1, it ultimately comes into one positions. Means a thermodynamic cycle where initial and final condition are identical. So the gas power cycles, Carnot cycles, all are like same. So it is a vapor power cycle. What is the difference in vapor power cycle? In vapor power cycle, we actually can see that two phase, means liquid and vapor, are working through the cycle. We'll go into the next session that how it is worked and so many things. So Rankine cycle mainly consists of 4 different processes. What are the processes? First of all, Rankine cycle, it is a reversible heat addition process. Reversible constant pressure heat addition process. Constant pressure heat addition process. We all know that constant pressure means the pressure will be same throughout the process. Second one is it's following a reversible adiabatic expansion process. The third one is again reversible, what we have seen at first, reversible constant pressure heat addition process. So the next one will be reversible constant pressure heat rejection process. And ultimately the last one, it will be reversible constant pressure, it will be reversible adiabatic compression process. So it is actually used in a thermal power plant. What is ultimately our output in a thermal power plant? To get an shaft work, where shaft work is coupled with alternator and ultimately it produces AC current. So what will be the TS diagram? Of this process? TS diagram, it is a liquid portion. We also called this portion is a vapor dome. Means it is here liquid and vapor mixture. This point is critical point. Critical point. If the condition is at first intro, then later on I will make you understand. So if initially the condition is 1 here, means it's in a reversible constant pressure heat addition process. The first process for the Rankine cycle is reversible constant pressure heat addition process. So we can see that this is constant pressure, and this point is dry saturated point. This point is dry saturated point. Saturated point for this pressure. Suppose it is a boiler pressure, so we can say it is P boiler. So at first we should discuss, and हम लोग बाद में चलते हैं इसके डिटेल्स स्टडी पे. हम लोग क्या देखें कि फर्स्ट प्रोसेस इज रिवर्सिबल कांस्टेंट प्रेशर हीट एडिशन प्रोसेस. So it is reversible constant pressure heat addition process, and after that it is reversible adiabatic expansion process and reversible constant pressure heat rejection process Q2, and ultimately it is reversible adiabatic compression process. So it's starting from 1 to 2, 2 to 3, 3 to 4, and it brings back into 1 again. So we can say it is a thermodynamic cycle. Now how this TS diagram is formed, or what will be the layout of a thermal power plant where this Rankine cycle operates, will come into this chapter. So this is the typical layout of a thermal power plant, where we can see that it is starting point 1. We are taking a dry saturated steam into the turbine, which ultimately produces a work WT and comes into condenser. So it is reversible adiabatic expansion process in turbine, which produces a shaft work of amount WT. It ultimately comes into condenser, where it rejects heat Q2. So we can also tell it is a constant pressure heat rejection process. It's ultimately it comes into the feed pump, where we give some amount of compressor work WP, and ultimately it gets into the boiler, where an amount of Q1 heat is given. So this cycle repeats. There is a water molecule which gets heated and ultimately we can say it is superheated and comes into the turbine, which produces a shaft work, and it goes into condenser, where it rejects an amount of heat Q2, and ultimately in a feed pump it taken a WP amount of, and this cycle rotates. And this diagram, this typical diagram, is represents, we have seen it before, that this TS diagram, where we can see this is the initial 1 point. It's the turbine reversible adiabatic expansion process 1 to 2, which produces a WT amount of work, and in a condenser it rejects an amount of Q2 amount of heat, in a pump, and WP amount of work is done to the system, and ultimately it's here 3 to 4. A 4 to 1 portion is a boiler portion, where Q1 heat is added. So if it is a thermodynamic cycle, if it is a thermodynamic cycle, so if it is a thermodynamic cycle, we can say that it's a cyclic process where heat addition is heat addition is Q1, where heat addition is Q1, heat rejection is Q2, as we consider it is a minus Q2 as per sign convention. WT amount of work is produced and WP work is given to the system. So ultimately what we can say in terms of efficiency, we can say that W from the second law of thermodynamics, we can say W net will be in terms of a heat input. What will be W net? Shaft work is WT. So we can say WT minus WP divided by Q1. As far we also know that summation of heat interaction equal to summation of work interaction. So we can also say that Q1 minus Q2, as far Q1 is taken as positive, it is heat taken into the boiler and heat is rejected through the condenser Q2. So it will be WT minus WP. So we can also transfer WT minus WP by Q1 minus Q2 divided by Q1. So it ultimately gives our efficiency equation Q2 by Q1. So ultimately we are getting an efficiency of 1 minus Q2 by Q1, efficiency of Rankine cycle. On it, we also have this equation from the second law of thermodynamics. Now next it will be your question, how this TS diagram is formed, right? So how this TS diagram is formed? TS diagram is formed so that for that condition you have to take in account, suppose we are hitting at minus 10 degrees centigrade of ice into 250 degrees centigrade of vapor. We will try to convert minus 10 degrees centigrade, which is a solid condition, into 250 degrees centigrade of a vapor condition. And what will be the process? We will just look into this matter. So we are going to heat it minus 10 degrees centigrade of ice into 250 degrees centigrade of vapor. So what will be the first step? Minus 10 degrees centigrade of ice, which is in solid form, it will take a sensible heat and ultimately comes into 0 degrees centigrade of solid condition. Means it remains in ice condition. What will be the second step? Now this 0 degrees centigrade of solid is taking latent heat and comes into 0 degrees centigrade of liquid form. Now again 0 degrees centigrade of liquid form, again it will take sensible heat and comes into 100 degrees centigrade of liquid form. Now 100 degrees centigrade of liquid will take latent heat of vaporization and it will ultimately comes into 100 degree centigrade of vapor form. Now this 100 degree centigrade of vapor condition will take the sensible heat and it will go on increasing its temperature as per our needs. So here we have taken minus 10 degree centigrade to 250 degree centigrade. So these are the following steps it will follow. So you get that minus 10 degree centigrade of solid, it will comes into 0 degree centigrade of solid by taking sensible heat, and this 0 degree centigrade of solid by taking latent heat of melting, it will comes into 0 degree centigrade of liquid. And this 0 degree centigrade of liquid taking into sensible heat, it will comes into 100 degree centigrade of liquid. Now this 100 degree centigrade of liquid taking latent heat of vaporization, it comes into 100 degree centigrade of vapor. Now this 100 degree centigrade of vapor again by taking sensible heat, it will comes into 250 degree centigrade of vapor. Here I forget to mention this total process is occurring at 1 atmospheric pressure. Total process is occurring at 1 atmospheric pressure. Now we give some points. Suppose this is condition 1 or point 1. It is point 2. Point 2 is same here, 2 to 3. No, this 3 to 4 is 4 to 5, and this 5 to ultimately 6. So if we plot a diagram of temperature versus entropy, we can say this is the starting point number 1, which is minus 10 degree centigrade of solid. You can see that minus 10 degree of centigrade of solid, by taking sensible heat, it comes into 0 degree centigrade. So the graph will be straight line. It will increase its temperature and corresponding entropy. That's what we know, that when heat is added to the system, the entropy of the system increases. So it comes into 2 number state, means 2 means 0 degree centigrade of solid state. Now this 0 degree centigrade of solid state, by taking latent heat, it comes into 0 degree centigrade of liquid, means the temperature will be remain same for 2 to 3 step, but entropy is increased due to this latent heat addition. Okay. Now this 3.0 degree centigrade of liquid, again by taking sensible heat, it will increase its temperature and corresponding entropy and comes into state number 4. State number 4. Again state number 4, by taking latent heat, it comes into state number 5. So it will again a horizontal line, state 5. Now again this 5 condition will be ultimately to 6 condition. And this total process occurring at 1 atmospheric pressure. Now this 1 atmospheric pressure, what is 0 degree centigrade solid, minus 10 degree centigrade of solid, rise, what is 0 degree centigrade of solid, rise, 0 degree centigrade of liquid, 100 degree centigrade of liquid, 100 degree centigrade of vapor, and 250 degree centigrade of vapor. So we will get this for 1 atmospheric pressure. So similarly for 2 atmospheric pressure, again if we start this diagram, and somehow we'll see the diagram will be like that. If we increase the temperature, the tendency will be somehow that. So these are all the same point. Number 1 point means minus 10 degree centigrade of solid, but with somehow it is in increased pressure. Suppose it is 180, it will be for 280, it will be for 380, So now, where is this 100 degree centigrade liquid forms these points? These liquid points are joined, these vapor points are joined, and if we increase the pressure, what will be the characteristic of this curve? This will somewhere joint, that will be added and becomes a point in the above. So what does it mean? 4 to 5, state number 4 means 100 degree centigrade of liquid ultimately by taking latent heat of vaporization comes into 100 degree centigrade of vapor. So this 4 to 5 is indicating latent heat, right? So from the diagram we are sure about the thing that if the pressure is increased, then the latent is reduced. Ultimately a point will be there where to convert liquid into vapor no latent heat is required. So this point comes as mentioning it critical point. What is the physical phenomenon of critical point? Means above the critical point or at critical point liquid flashes into vapor without taking any amount of heat. Okay? Means without taking any amount of latent heat, the fluid converts into vapor. Now we will define saturation point. Saturation point. What is that? Saturation point. Saturation point is something, a phase from which a change of phase may occur, or a point or a state, rather it can be defined as a state from which a change of phase may occur. So where a change of phase may occur? From the point we can say that here minus 10 degree centigrade solid, so 0 degree centigrade solid. So here, is it here the phase is changing? No. Next point, 0 degree centigrade solid converting into 0 degree centigrade of liquid, means this is a phase change process. What will be the next? 0 degree centigrade of liquid, 100 degree centigrade liquid, both are liquid. So it's not. Again 100 degree centigrade liquid converts into 100 degree centigrade of vapor, means it is a phase change point, right? So from the definition, what was our definition? The state from which a change of phase may occur, means here from starting point to it is a phase changing point, and starting point 4 it is a phase changing point. So we can say that 2 is a saturation point, 4 is saturation point regarding the heating of minus 10 degree centigrade of ice into 250 degree centigrade of vapor. We are getting 2 saturation point. Now what is the condition of the saturation point? The saturation point means at condition number 2 the phase is solid. So we can also say it is a saturated solid state. Saturated solid state. And what will be the point here? Is a saturated liquid state. Now, if the process is reverse back, means if we had to convert 250 degree centigrade of vapor into minus 10 degree centigrade of ice, then what will be that? That will be same process. In the above case, it is taking heat, it will leaving heat, it will reject heat throughout the process. So what will be the first condition? That condition will be 250 degree centigrade of vapor rejecting the sensible heat comes into 100 degree centigrade of vapor. Again 100 degree centigrade of vapor by rejecting latent heat comes into 100 degree centigrade of liquid. 100 degree centigrade of liquid by rejecting sensible heat comes into 0 degree centigrade of liquid. 0 degree centigrade of liquid by rejecting latent heat comes into 0 degree centigrade of solid or ice. 0 degree centigrade of solid by rejecting sensible heat ultimately comes into minus 10 degree centigrade of solid, which is our desired condition. Means here also a phase change is occurring. Where the phase change is occurring? Look at that. 100 degree centigrade of vapor changing its phase into 100 degree centigrade of liquid. So here we are getting a phase changing state, and another one is 0 degree centigrade of liquid is converting into 0 degree centigrade of solid. So these are the 2 points when we are reversing back the total situation. So that condition, that will be a saturated point, and that will also be a saturated point. What is the condition here? At saturated point it is vapor form, so it is saturated vapor state, and it is saturated liquid state. So from that figure we are getting 4 saturated points: saturated solid state, saturated vapor state, and 2 saturated liquid state point. Now to distinguish these 2 saturated liquid point, we are considering when the process by taking the heat when minus 10 degree centigrade of ice is converting into 250 degree centigrade of vapor. What was that point? 100 degree centigrade of liquid converting into 100 degree centigrade of vapor. So the process is vaporization. So we can say that saturated liquid state with respect to vaporization. Okay. Now there is a saturated liquid point, and this process is during the reverse back. And what is here? The 0 degree centigrade of liquid is converting into a solid state, means it is a process of solidification. So we can say that saturated liquid state, this state with respect to solidification. When this becomes total hazing, there is some problem. Still, if you have any question, you can ask me later. Okay. So we are getting 4 saturated points. Okay. Now this is our concerned area. Why this is our concerned area? This is the liquid portion, this is the vapor portion, this is the liquid portion, this is the vapor portion. Means left to all is liquid portion, and right of this line is vapor portion. Because in a thermal power plant we have water and steam condition. That's why this portion, this liquid and vapor flow is very much important. That's why in TS diagram we are representing the Rankine cycle in this phenomenon. Similarly, the PV-HS diagram, also called as Molière diagram, you can see there is also, you can draw it. All the things you can available in beginner book, or you can also get through the video lecture of Somen Mrs. Okay students, this is it for today's class. We will go through different naming like reheating, regeneration in further classes. Also we can know about the
the use of steam tables on how the efficiency equation can be converted into enthalpy based equation, because as we know that now this all these devices are boiler, turbine, condenser and feed pump. All devices are steady flow devices. So the ultimately efficiency equation can be converted into enthalpy equation. In terms of enthalpy, we know that WT is can be mentioned or declared in terms of H1 and H2. If the